Alright, so we have chapter 24 here, which is in geometric optics. So the geometric optics allows us to pretty much solve the problems that are related to light interacting with things like mirrors and lenses. So that's what we're going to do. So study reflection from a plane surface, like a mirror surface, and reflection from a spherical, mirrors. So basically the first part of this chapter is on mirrors. So we're going to look at flat mirrors or plane mirrors, and then curved or spherical mirrors. Understand how to use the ray diagrams to refine the image that generated of the object, using the mirrors, and then use that to find, let's say, what type of mirrors gives us real images, what types of mirrors gives us virtual images, because when you're talking about image generated or for the object, then we can look at in terms of two types of images. There are real images, there are virtual images, and some mirrors can give us real images, some mirrors can give us virtual images. Then we're going to use the, let's say all the equations and the concept more or less that we develop in the first part and apply that to lenses. And we're going to see that there are a lot of similarities and some differences, and we're going to talk about all the similarities and differences and how we can then use the same ideas in terms of ray tracing, in terms of using the ray diagrams to find image generated by the lens this time. And also we're going to very shortly at the end talk about the human eye. In any case, so here's an image of a surgeon performing microsurgery. And one thing we know that, let's say, they're using, let's say, a microscope, right, that actually maximizes the image, or enlarges the image. So there's a magnified, let's say, image of the object that they're looking at. So we're going to talk about what type of lens should we use for, let's say, this type of surgery. And there are, two types of lenses, two types of mirrors that we're going to be considering. And we're going to know at the end of the class, or at the end of this chapter, right, what type of lens would be good for, let's say, this type of surgery. Alright, so one thing we're going to do here is start probably with the easiest one, which is the reflection at the plane surface. So what we have here is we have an object. An object basically is something that can, let's say, generate light. Okay, so you can see, right, this point here is that where our object is. So the object technically can be a point, or can be something that has a size. So right now we start with something that has a point, and what we have here is that particular object, right, is generating light in every direction. So when we talk about object, we have, again, sort of like two types of objects. One type is, let's say, a source that generates its own light, sort of like the lamp or the sun. And then we have different type of objects that reflect the light that is generated by something else. So for us, in a way, it doesn't really matter what we're using for the object. Could be, let's say, natural source, or it could be a reflective source. So for example, right now, if you're sitting in your room, the lamp is a natural source. It generates the light. Everything else that you see is a reflective object. That means they reflect the light, generated by a natural source. You can still see them, because when the light is reflected from that object, it reflects basically in such a way that eventually reaches your eye. So that's why if you go and turn off the light, you're not going to see any of those objects, because they no longer reflect that light. So in a way, what we have here is our object can be one of those natural sources, or reflective sources, doesn't matter, as long as we understand that it's an object that reflects light. So then all those rays starting from our object, either natural, let's say, light, or the reflective light coming from the object. And one of the things we have here is we're then going to start using, let's say, law of reflection, law of refraction, to understand interaction of that light with the surface of a mirror or a lens and things like that. So for now, what we have here is a mirror, and it's a flat mirror or a plane mirror. That means it's basically its surface is has no curvature pretty much. And the plane mirror, just like any other mirror, reflects all the light. So it reflects all the light. That means what I have here is, so let's say you can see, right, this is the light that kind of diverges away from the source, right, diverges away from the source. And for example, when this light hits the surface, see, we can use that law of reflection and see that it reflects back. Same thing with the second, it reflects back. Again, law of reflection using, right, so you can see, right, all of them reflect back. Now, one thing we have here is, if you're an observer and you're not directly looking at the object, you can still see the image generated by the object if you look into the mirror. Because, for example, this reflected light will reach, hard to do it, this reflected light will reach the eye of the observer, and what we have here is the mirrors have the ability to then generate the image of the object in the mirror, or basically using that reflected light. So what we do here is you trace this reflected light into the mirror and use let's say more than one ray to kind of see where all of those rays converge or intersect. So you can see, right, if you use all of those reflected rays, you should be then able to see that they all kind of behind the mirror, right, behind the mirror, appear to be converging. You can see, right, in front of the mirror, none of those rays will converge or intersect. They're all, diverging away from the mirror. But behind the mirror, they appear to be converging, and it appears like that those reflected lights actually originate from that point. Okay, and that point is basically the image point. That means what we do here is taking the P to be the object's point or object's position, right? Then we can use this reflected rays to map up, right? So basically trace back and find the image point. Okay, so for all the plane mirrors, this is basically what we're going to be doing. That means look at two or more rays that are reflected off of the surface of the mirror, then trace them back behind the mirror, right, in the back of the mirror, and we will always find point where those rays converge or intersect, right, and that's going to be the image position. All right, so you can see, right, the reflected rays entering the eye look as though they had come from point P prime. So generally, prime represents basically the image point. P is for the object point. All right, so we can kind of understand that you don't need all those rays to find the position of the for the image. So usually two rays are enough. You can use third one to verify, but let's say if it's a mirror, generally 2 or 3 is more than enough. Here what we have, so let's say again going back, right, this is the object, P represents the point of the object, and you can see, right, I am using here 2 rays. One is moving like this, hits the surface with respect to the normal, then it reflects back. So when it reflects, this is the one that basically going to reach the observer's eye. So then if I trace that one back, it's going to go like this. Okay, but you can see, right, it extends infinitely. So now I need another ray so that I can use to intersect that first one. And I can use any one of them. But one easy one is that it goes, perpendicular to the surface, hits the surface, that means along the normal line, and then it reflects back on itself. Remember, theta A and theta R basically the same, right? Law of reflection. So if this reflected light, so this is this reflected light, if I trace it back, in the back of the mirror, then I can see that first and second rays intersect at that point, and that's my P prime. That means I will take then some measurements where I take the position of the object relative to the mirror to be object distance, and we represent that with S, and then the position of the P prime, which is the image position, relative to the mirror is going to be then represented as S prime, and that's going to be then the image distance. Now you can see, right, after reflection, all rays originating at P diverge from P prime. It seems like all those reflected rays are originated at P prime and then diverging away. So when the image appears to be diverging from some source point, like in this case P prime, that's usually indication that this image here is virtual. That means you can see, right, those rays in the back of the mirror that we, trace back, right? So those are, like this two over here, which appear to be starting at P prime. They are not actual rays. They are not actual rays. None of the actual light goes back into the mirror. That means this is known as a virtual image, because light has to go through the point of image in order for that image to be a real image. But here those lights reflect, and go and diverge in front of the mirror, and none of those lights go back of the mirror, but image is formed in the back of the mirror. That means it's a virtual image. All right. So, and one of the things we can do here is, if we kind of look closely, let's say here we have two positions. This is basically is the object distance, and this one here is the image distance. And one of the things we're going to do here is, this is going to be true for all the mirrors, is that object distance S is positive because this object is on the same side as the incoming light, which is the front of the mirror. That means, if I have the object 5 centimeters distance in front of the mirror, then I will write this S is equals to 5 centimeters, and it's going to be positive. Now, image distance S prime is going to be negative because the image is not on the same side as the outgoing light. Again, outgoing light, you can see, right, is in front of the mirror, and image is formed in the opposite side. So then S prime is going to be negative. And for the plane mirror, S prime is going to be equals to, exactly, S in terms of its magnitude, but S prime is going to be negative again, because as I said, right, distance to the image is negative because this is image that is not on the same side as outgoing light. You can think of like the front of the mirror is the positive side, the back of the mirror here is the negative side. And if the image is in the back of the mirror, its distance is negative. So that's why we can say that S equals S prime, but if you put absolute value, they are equal to one another in a way they're in their magnitudes. Alright, that means every time you have an image that is in the back of the mirror, its distance is going to be negative, plus it's going to be virtual. Okay, you can always assume this. If you have an image that is formed in the back of the mirror, it's a virtual image. Again, why is it a virtual image? Because none of the actual outgoing light rays go through that point P prime, right? So we have to kind of virtually trace them back to appear to be originating at point P prime. All right. So you can also deal with an object, right, that is not a point, but it has a finite size. So in that case, what we do here is we have let's say an axis that we can draw. So you can see, right, so this axis over here is the axis that goes sort of like through the center of the mirror, and we have then the object not only given the size but also the orientation. So you can see, right, the object here is given as an arrow pointing up, so it's upright. And what I have here is its position is S, which is the object position relative to the mirror, and we also now have the size, which is Y. So the Y is its vertical, right, height, you can say. So the height of the object is given with Y, and when you find the image of this object, then it's going to be given with Y prime. And what I do here is, again, I use two rays. So those two rays are going to be, you can see, right, so one is going to be straight hitting the surface of the mirror and then reflecting back, right? So this is basically the easy one to do. The other one that is, relatively straightforward for us to do. So see where this axis, right? So this axis here goes through the mirror. That point is known as the vertex. Okay. So then you can use another ray that goes and hits the vertex. So when it goes, hits the vertex, so you have again low reflection, so it's going to reflect back like that. Now what we do here is, you can see, right, this is ray 1, this is ray 2. They're not going to converge in front of the mirror. So you have to trace them back. So you trace them back, and then you can see, right, if I take Q to be the tip of the arrow of the object, then Q prime is the tip of the image in that case. And I can see that in order for me to generate the image, I have to do an arrow like this, right, until it reaches this Q prime. And looking at the size of the image, then I can represent it with Y prime. So Y prime is the image size. Now, to compare the size of the image and object, what we do here is we calculate lateral magnification. And this is just a ratio of Y prime over Y. And this magnification will tell you if the object and image have different sizes, right? So let's say you can see, right, if you get magnification is equals to, so for example, right now, if I look at Y prime and divide by Y, if Y prime and Y have the same size, then what I get here is I get 1. That means magnification 1 means Y prime and Y are equal to one another. That means image is the same height as the object. I also technically get positive 1. Positive 1 means that image has the same orientation as the object. That means both of them are inverted. So, sorry, both of them are upright. Generally what I have here is virtual images will always be the same orientation as the object. Okay? Whenever you're dealing with a virtual image, it's going to be exactly same orientation as the object. If the object is upright, image is upright. If object is inverted, image is inverted. That means all the virtual images are going to have the same orientation. Doesn't necessarily mean that, let's say, all the virtual images are going to be the same size. It is true for the plane mirror. So this is always going to be true for the plane mirror. I doubt any of you have seen a plane mirror, flat mirror, where you stand in front of it and you have, different height. Okay? If there is the case, that means the mirror has a little bit of curvature that may be negligible for your eye, but it's there. Okay. So this is the, again, equation for the magnification, and magnification tells you two things. It tells you the size of the image compared to the object, and also orientation. So generally when the magnification is plus, that means you have an upright image. When magnification is negative, you have a basically inverted, right, image. Alright, so let's look at this example over here. So we have, let's say we have 1.62 meter tall person, right, and we want to be able to see your full image in a vertical plane mirror. What is the minimum height of the mirror that will meet your needs? Well, one of the things we have here is, if you're standing in front of the mirror like this, the minimum height of the mirror, that means its size, right, should be about, half the size of the object. Okay, that means for part A, right, so for part A, what I have here is, if I'm looking at the size, then the size should be exactly half of your height. That means, let's say, this is for the mirror, not necessarily the image, right? So H, right, so the mirror should be half your height. So let's say in this case, 0.81 meters. Alright, so part B. How far above the floor should the bottom of the mirror be placed, assuming that the top of your head is 14 centimeters above your eye level? And we're going to use a ray diagram to explain. Well, here's what I have. The mirror should be located such that you be able to see the top of your head and, let's say, your toes, right? But it doesn't have to be the same height as your, top of your head, or the same, altitude, right? Because in order for you to see the top of your head, so let's say, I don't know, let's call this Q, right? So what you need to do here, you understand that the light from the top of it will reach the top of the mirror and then reflect back. That means it doesn't have to be, see, this is 14 centimeters above, right? So it doesn't have to be 14 centimeters. It can be like, let's say, half that. Okay, half that size. Same thing is here. So the mirror doesn't have to be, extending all the way down, because to see your toes, you have the light hitting the, bottom of the mirror and then reflecting into your eyes. That means this can be then the half of your size. Okay. That means it can be only 7 centimeters above your eye level, right? And it can be, let's say 74 centimeters below. So that means, for example, if you assume that this is only 7 centimeters here, right? So let's say this is your eye level. So this can be only 7 centimeters. And then that means it lifts from here to there 185. Sorry, 155. 155, which is 162 minus 7, right? 165. That means from your eye level to the ground. And as we said, right, so this then, since the mirror itself is 8.81 meters, or, let's say this is 1.55 meters. All right, so let me... So 1.55 meters. So this is then, let's say, 0.07 meters, and this is 0.81 meters. That means then this distance is the difference then of 1.55 minus 0.81. So we get 0.74 meters. That means this distance, right, from the ground should be 0.74 meters. That means if it's 0.74 meters above the ground and 7 centimeters above your eye level, then you'll be able to see basically your entire body. All right. So let's look at then curved mirrors. So the curved mirrors are basically come in two shapes. Okay. So you can, also known as spherical mirrors, because one thing you have here, you can have a sphere and kind of carved, you can carve two parts. Let's say you can do this size of this part of the, a mirror, like, let's say if it's a spherical mirror, right? Or you can do this part. Okay, so depending on which side you're doing. So either this or that. So that's why, depending on that shape. So you can see, right, if I'm using this, then I have that shape over there. Okay, so this is known as concave mirror. Okay, so that's a concave mirror. Okay, and this side is known as a convex mirror. Okay, so depending again which side of that sphere are you using, that's why they're known as a spherical. And you can also see that if you are looking at sort of like, let's say, this part of the sphere, then this is being the C center, then the distance from the center to the mirror, right, is the radius r. So let's say you can see, right, if I'm using this as my, concave mirror, then what I have here is I do my, axis here, right, and what I have here is there's a vertex point, and C represents then the curvature of this, of this sphere, of this mirror. And radius, you can see, right, if I take from this distance to the mirror, that's then the radius. Okay, like that, sort of like to the center. That's my radius. And that particular value is independent if there's an object there or not. You can see, right, even if I don't have an object, I can measure the radius r for that, let's say, spherical mirror, because it just depends on its geometry. Okay. Now, one of the things we have here is this. So let's say you have a object, and it's a point object. Okay, so generally it's easier to start with the point object. So one thing we have here is, if I take the point object, and if I, use two rays coming from this point object. Remember, this point object generates, rays in every single direction. But we only need two or, maybe three to find the image generated by this object from the mirror. Then what we do here is, let's say this is ray 1. So you can see, right, ray 1 moves like this, hits at point B, the surface at point B, and then reflected back. See, now it reflects back in front of the mirror. And then I use any other ray. But let's say one is easy when I use that, let's say the one that goes straight to vertex, hits the vertex, and reflects back on itself. Alright. Sorry, that wasn't very good. But let's say kind of goes like this and reflects back. And you can see, right, both of those, so if I clear all this, right, both of those converge at that point P prime. That means you have two real light rays converging at that P prime. That means P prime is the image position, and it is, you know, due to two actual rays intersecting at that point. That means I can take that position, right, P prime, and use that to find then image position, and use point P to find then the object position, and use curvature C, where that, you know, gives me the radius, right, of this sphere. Then I can use that to find basically the, what we call the equation for the mirrors. So this guy over here. That means 1 over the object distance plus 1 over the image distance is equals to 2 over the radius of that spherical mirror. Okay. Now what I have here is, you can see that this radius for this particular sphere, and remember, this is concave sphere, right? So the concave sphere, you can see, right, this point C is in front of the mirror. Remember, in front of the mirror was a positive, you know, side of the mirror. That means R is positive for concave mirrors. Okay, so R is positive for concave mirrors. And look at what I have, right? Image here, this P prime, right? You know, image is also in front of the mirror. That means S prime is also positive for the concave mirror. That means I have image position positive, radius positive, right? Because both of those things are in front of the mirror. And this equation is known as the object-image relationship, or spherical mirror equation. Now, so technically this also works for the plane mirrors, because what I have here is this. So 1 over S plus 1 over S prime equals 2 over R, right? Now, what I have here is this. So think like this. So let's say this is my curved mirror, and this is the radius. See, if I make curved mirror a little bit, you know, extended, right? That means I increase the curvature part, the radius increases. If I increase it even more, the radius increases even more. And if I continue increasing until I get flat surface, then it means that the radius is increased so much that the radius is extended all the way to infinity. So this is for the plane or flat mirrors. Now, what does it mean in terms of this spherical mirror equation? Well, if R is infinity, the right side of the equation becomes 2 divided by infinity. And hopefully you guys know, right, if anything divided by infinity gives you 0. That means 1 over S plus 1 over S prime equals 0, means 1 over S equals negative 1 over S prime. And if I then do inverse of both sides, I get S is equals to negative S prime. And that's exactly what we talked about, you know, for the plane mirrors. So that's why image is the same distance from the mirror as the object, but in the opposite side, right? In the back of the mirror for the plane or flat mirrors. All right, so but for example, like let's say if you're considering then this particular type of, you know, curved mirror, then what we get here is basically, okay, so the two types of, right, mirrors that we have here, curved mirrors, is the concave, okay, and this one here is convex. And you can see what we have here is concave mirror has a point C is in front of it, so radius is positive. And look at convex mirror. Convex mirror has point C in the back of the mirror, so R is negative. Okay, and what we have here is, depending on the position of the object in front of the mirror, for example in this case, you can see, right, the outgoing light, which is reflected light, basically can actually generate, you know, a real image for us, where for the, you know, convex, we're going to see that when the light hits the mirror, doesn't matter where it is, right, they're all going to diverge away from one another. Alright, so as they diverge away from one another, then eventually we're going to see that if we're talking about the, let's say, convex mirror, you're always going to get a virtual image. Okay. Anyway, so we'll get to that. But in this case, just make sure you guys understand that you have this radius quantity, right, is positive always for concave and negative always for the convex. Okay. So that's kind of like how we get this, you know, radius r, because radius r is important, right? So in this equation, 1 over s plus 1 over s prime equals 2 over r. So if you don't have r as negative, you're going to get the values wrong. Now let's look at then concave mirror and assume that we're dealing with the object that is infinitely far away. When we say something is very far away, you can say that's almost the same thing as infinitely far away. Then what I have here is the infinitely far away also means that the distance s, right, is equals to infinity. And that means then the image that will be formed has a rays that coming as parallel to one another. Then when they hit the, or strike the, let's say, the surface of the mirror, they're all going to converge like you see in this image over here. They're all going to converge to some point, and that point actually happened to be exactly half of the radius distance, and what we do here, we call that point a focal point. Okay, so that becomes the focal point. And then the focal point is then exactly half of the radius distance, and its length here is known as a focal length. Okay, that means capital F is the focal point, lowercase f is the focal length. And you can see, right, all the light rays converge at that focal point. Since they all converge at that focal point, that's where the image will be generated. That means for this particular case, the beam of incident parallel rays converges after reflection from the mirror to a focal point. And the distance from the vertex to the focal point denoted by lowercase f, so again it's known as a focal length. Okay, and what we have here is then this particular case, right, when s is equals to infinity, then s prime is equals to f, because when I'm using this 1 over s plus 1 over s prime equals 1 over f, if this s is infinitely far away, 1 over infinity equals 0, then you have 1 over s prime equals 1 over f, which means s prime is equals to f. So in this case, image will be formed at the focal point.